Okay, here's the recording in progress. We'll go ahead and start. All right, so I'm about a day ahead. I'm just about to finish 11.4, or I'm starting, the alternating series test. 11.5, and I may even finish it today, but we'll see how it goes. Okay, tomorrow is our quiz. It's only Thursday, but we'll have a holiday on Friday, so I'll give you the quiz tomorrow. Do 11:59 p.m. tomorrow for the quiz. Usual rules apply. Okay, so we only have one more chapter. I'm about a day ahead right now, but we'll see how it goes. Can keep this as iffy. I may change the last regular test from the 9th of December to the 10th. But in any event, the final exam is going to be on the 17th, 8:10 to 10:40 a.m. Okay. All right, so 11.5 is not really that long of a section, so I may be able to knock it all off today. It's on the alternating series test. So let's get started with that presently. Okay, so I gave an introduction to it last time. Alternating series tests, AST is our abbreviation. If a series is alternating, my abbreviation is alt. Absolute value of A sub n decreases, arrow down. Okay, the terms decrease in absolute value, and A sub n's approach 0. Here's the abbreviation that you will write for me on homework and quizzes and tests. Alternating, alt, absolute value of A sub n decreasing, A sub n approaches 0. You can even put this on your cheat sheet if you wish. Just give me that exact language if you think it applies. Okay, then the series converges by the alternating series test. Okay, so here's our first example. Summation n equals 1 to infinity of -1 to the n plus 1 over n. Okay, you should know that when you see that -1 stuff, that's going to make it alternating, right? And the n plus 1 is just to assure, do I want the first term to be positive or negative, as the case may be, depending on where you start indexing. So if I plug in 1, I have -1 squared, which is 1 over 1. Plug in 2, I have -1 cubed, that's -1 divided by 2. So it's 1 minus a half plus a third minus a fourth. This is the alternating harmonic series, right? Now the regular harmonic series, they're all pluses. 1 plus a half plus a third plus a fourth and so on. We know that diverges. But what about the alternating harmonic series? Well, is it alternating? Well, sure. The terms decrease in absolute value. And it's an absolute value. If you didn't have the absolute value, then obviously it always goes increasing, decreasing, increasing, decreasing, right? It goes plus, minus, plus, minus, plus, minus. So anytime you go from a plus to minus, it's automatically decreasing. And anytime you go from a minus to a plus, it's automatically increasing. Okay, so the argument here is in absolute value. Okay, ignore the signs. 1, a half, a third, a fourth, a fifth. Okay, that's decreasing. And A sub n approaches 0. They do. Okay, so therefore, the series is convergent by the alternating series test. So even though the harmonic series, the regular harmonic series, which goes 1 plus a half, plus a third, plus a fourth, that diverges, the alternating harmonic series converges. Okay. Right now, we're not prepared to say what it converges to, but we'll see later. It actually, believe it or not, this turns out to be natural log of 2, which is about 0.6931. And I'll actually show that to you later. Okay. And that does seem kind of weird. These are just fractions, the reciprocals of the integers where it's alternating, and yet it comes out to be natural log of 2. Okay, but let's just see if it's kind of reasonable. 1 minus a half, that's 0.5. 0.5 plus 0.3, that's like 0.8. 0.8 something. Subtract 0.25, so 0.58 and 1. So it seems reasonable that it would converge to somewhere around 0.6931. Okay, so now for some problems. Number 3, -2/5 plus 4/6 minus 6/7 plus 8/8 and so on. Now the series is alternating, but the A sub n's do not approach 0. Are these terms decreasing in absolute value? It doesn't look like it. 2, 4, 6, 8, 10, 5, 6, 7, 8, 9. Looks like we keep adding 2 to the numerator, but keep adding 1 to the denominator, so it's not going to approach 0. So if the A sub n's do not approach 0, ... therefore the series diverges by the test for divergence. Okay, so remember back in section 2, the test for divergence. Okay? If the a sub n's do not approach 0, you automatically have a divergent series that would test for divergence. Okay. Okay, 5 star. I don't think this is the same as our regular 5. Let me check. It's not. That's okay. All right. Well, this again normally is a dead giveaway that your series is going to alternate, right? That -1 thing, either to the n or n minus 1 or n plus 1. And then let's see if I plug in n equals 1, that makes this -1 to the 0. That's positive. So it's going to go plus minus plus minus. So it's alternating. Okay, plug in 1, it's 1/3. Plug in 2, it's 1/5. Plug in 3, it's 1/7. Plug in 4, it's 1/9. And we already know it's alternating from this. So 1/3 minus 1/5 plus 1/7 minus 1/9 and so on. Okay, so it's definitely alternating. The absolute value of a sub n decreases. The terms are decreasing in absolute value. 1/3, 1/5, 1/7, 1/8. They're getting smaller. And they approach 0. So therefore, ... means therefore, the series is convergent by the alternating series test. And you can just write this, save yourself time. You don't have to write out the series converges by the alternating series. It takes too long. Okay, there's a shortcut way of saying the whole thing. If we agree, that's what we mean. And the ... means therefore. In logic, therefore. Okay. So of course, in order to use the alternating series test, the first thing you want to think of is it alternating, right? And if you see the -1 stuff, you're pretty sure it's going to be alternating, although that's not a guarantee. And there's actually another case where it's alternating, but you can't tell right away. And I'll show you that. That happens to be problem 15. I'll show you that in just a moment. Okay, 7. Summation -1 to the n, 3n minus 1 over 2n plus 1. Okay. Notice I used a lazy notation of not putting n equals 1 to infinity. Sometimes that's okay if all you care about is the series itself. All right, is it alternating? Sure, this is. But what happens to a sub n, or the absolute value of a sub n? So ignore the -1. When n gets super big, we know the way the game works, that -1 is insignificant. The +1 is insignificant. It's 3n over 2n, which is 3/2. That's not 0. The a sub n's have to approach 0. They don't. The absolute value of a sub n approaches 3/2. Okay. So in the long run, it looks like 3/2 minus 3/2 plus 3/2 minus 3/2. That diverges. Okay. Remember, divergence doesn't mean necessarily goes to infinity, although a lot of times that's true. It just means we do not approach any single number. So if I look at the partial sums, this is 3/2, 0, 3/2, 0, right? It bounces back and forth between 3/2 and 0. So we do not approach any one number. So the series diverges by test for divergence. In the long run, it looks like 3/2 minus 3/2 plus 3/2 minus 3/2. Okay. You could do L'Hopital's rule for the limit. Okay, but essentially the -1 and the +1 are insignificant. Okay, remember n is getting super big. If n is 1 billion, if 3 billion, okay, what's 3 billion divided by 2 billion? 3 over 2. I say, oh, it's 3 billion, take away 1. It's still 3 billion, right? And 2 billion plus 1, it's basically still 2 billion. The ratio is essentially 3 over 2, right? I guess the logic again is if you have $3 billion, take away $1 or add $1 is not that big a difference. You basically still have $3 billion, right? Okay. All right, 11. Summation n equals 1 to infinity, -1 at n plus 1, n squared over n cubed plus 4. Okay, this should be fairly straightforward. Is it alternating? Yes, that -1 stuff tells you. What's the n plus 1 do? Well, it means you're starting off with a positive. Plug in 1, 1 plus 1 is 2. So it goes plus minus plus minus. Are the terms decreasing in absolute value and approach 0? Sure. In the long run, you basically ignore the 4, right? So n squared over n cubed, that's like 1 over n. That decreases in absolute value and approaches 0. So therefore, the series converges by the alternating series test. Okay, now 15 is a little bit tricky because you might say, I don't see that -1 thing. Right? Once you see that -1 thing, it's almost a dead giveaway that the series is alternating. What's this sine of n plus a half pi stuff? Let's just try it. Plug in 0. I have sine of half pi. Well, that's pi over 2. Sine of pi over 2 is 1. Plug in 1. 1.5 pi, that's the same as 3 pi over 2. Sine of 3 pi over 2 is -1. Plug in 2. 2.5, that's the same as 5 halves or 5 pi over 2. Okay, that's coterminal with pi over 2. So I'm back here again. Get this focused here. And the sine of 5 pi over 2 is +1 again. And if I plug in 3, that gives me 3.5 pi, which is 7 pi over 2. That's all the way around, and another 3 pi over 2. That's -1. So this is a sneaky way of getting the series to alternate. This is equivalent to that -1 thing. It just looks a little bit more weird. So yes, this is alternating. It does go 1, -1, +1, -1. And then the rest of the stuff is pretty much the same. Okay? The terms decrease in absolute value and approach 0 quite clearly. Square root of 0, square root of 1, 2, 3, square root of 1,000,000, square root of 1,000,000,000, right? And if you add 1, that also makes it smaller. So the series is alternating. Absolute value of a sub n decreases and a sub n's approach 0. Therefore, the series converges by the alternating series test. Okay, then 19. We've done some factorial stuff. We haven't done too much with n to the n. Let's think a little bit about n to the n. Okay, is it alternating? Sure. Starting with a positive or a negative, we plug in 1, it's negative. So minus, plus, minus, plus. Okay, so I'll write some of the terms out. If I plug in 1, I have 1 to the 1 over 1 factorial. Let's do the denominators first. 2 factorial, 3 factorial, 4 factorial, right? Now the numerators, 1 to the 1, 2 squared, 3 cubed, 4 to the 4th power, right? Does it look like the terms are decreasing in absolute value and approaching 0? No, they're not. But the top stays bigger than the bottom. The next one is going to be 5, 5, 5, 5, 5 divided by 5, 4, 3, 2, 1. The top's going to win. The next one, you'll have 6 sixes on top. The bottom is 6, 5, 4, 3, 2, 1. So a sub n's do not approach 0. Therefore, the series diverges by the test for divergence. Okay, one more theorem in this section. Useful theorem, alternating series estimation theorem. Too much writing. ASET, A-S-E-T, alternating series estimation theorem. Okay, given a series which satisfies the alternating series test, okay, like this. In general, we're normally not going to be able to figure out how to add infinitely many terms easily. So we stop somewhere. So if we stop after n terms, we say, oh, you're cheating. You're supposed to go infinitely many terms. You know, I can't count infinitely many terms unless there's something about this series that I can figure it out. I have to stop after 10 terms, 100 terms, 1,000,000 terms. Okay. Oh, you're cheating. You're throwing out all the terms at the end. Well, the alternating series estimation theorem says if we stop after n terms, the error is no more than the next term, a sub n plus 1, in absolute value. Okay, so if we stop somewhere, the error is no more than the next term in absolute value. I'll show you the text version of this. And then we just have a couple problems involving that. Page 735, alternating series estimation theorem. So what it has is equivalent to what I say, but you may not get this. So this basically says it satisfies the alternating series test. Okay, it's alternating, the terms decrease in absolute value and approach 0. Then absolute value of r sub n, the remainder, is less than or equal to the next term in absolute value. Okay. To go over a proof of that, I'll just do a plausibility argument once again. So go back to this analogy that I gave yesterday. It's on page 733. Right? So go like that. So the fact that it's alternating means it's going to go left, right, left, right, left, right, right. The terms decrease in absolute value. So every time I turn back the other way, I go back less. Okay, so I'm going this way, and then I go that way, and then I go that way, and then I go that way. But each time I turn back, I don't go as far. And then the amount that I go tends towards 0. So we converge to some number s here. I cannot add up infinitely many terms. I say I will stop after so many terms. Okay. So if I stop after so many terms, the error is no more than the next term, which kind of makes sense. So let's say I go B1 and then go negative B2 plus B3 minus B4. Okay, and I say I don't feel like adding more. I stop right here. Here's the true value. The error is no more than the next term in absolute value. So it's no more than this. And you can see that makes sense, right? Because the term that it's converging to is S. The actual error is here. I'm going beyond that by choosing this next number. Same thing works if I go on to B7. B7 will pass the sum. It would come back over here somewhere, right? And then, so each time as I keep going back and forth, it'll be above, below, right? Because of the nature of the alternating. Right? So every time I go left, I'm smaller than the value. Then every time I go right, I'm bigger than the value. Okay? So if I decide to stop anywhere, if I stop after 5 terms, the error is no more than the 6th term in absolute value. If I decide to add 1,000,000 terms, which is easy to do on a computer, let a computer do that, the error is no more than the 1,000,001st term. So the error is no more than the next term. So given a series which satisfies the alternating series test, if we stop after n terms, the error is no more than the next term in absolute value. Okay, so I'll just show you a couple problems with that, and that's pretty much all we have. Okay, so these are the problems at the end. And then I'm pretty much done with the section. So 23 and 25 are similar. I'll do 23. And 27 and 29 are similar. I'll do 27. Okay, show that the series is convergent. How many terms of the series do we need to add in order to find the sum to the indicated accuracy? Okay, -1 to the n plus 1 over n to the 6. Absolute value of the error is less than 0.00005. Okay. Okay, so here's the series. Starts off positive. Plug in 1. 1 plus 1 is 2, -1 squared. So 1 over 1 to the 6 minus 1 over 2 to the 6, and so on. Alternating, yep. Terms decrease in absolute value, yep. Terms approach 0, yep. Therefore, the series converges by the alternating series test. Okay, so what is that approximate sum, okay, to an error of 0.00005 or less? So I keep going until I find a term that's below this. Okay, and on a calculator, 1 over 6 to the 6 is something like this. Let me see if I can verify that on my calculator. 1 divided by, well, let me do 1 divided by 5 to the 5th power. It's 3.2 times 10 to the -4. That's 0.00032. That's not quite good enough. So I'll do 1 divided by 6 to the 6th. 2.14 times 10 to the negative 5, that's 0.00002, roughly. Okay, that is less than 0.00005. So that means I can just add up these 5 terms. You say, well, that's not fair. You're supposed to add up infinitely many terms. That's right, but my error is no more than 0.0005. Okay, so how many terms do I need? I need 1, 2, 3, 4. I just need 5 terms to answer the question. How many terms we need? Add the first 5 terms. Okay, and I did it. Save time. I'll just show you the result. It was 0.000064. That minus that plus that minus that plus that. Okay. You see what we're doing? We're saying, hey, you're supposed to add up infinitely many terms. You only add up 5. So there's going to be some error. Correct. The error is no more than this by doing this thing here. Okay, so that's all it means. All right, then 27. Then I'm done. Approximate the sum of the series to 4 decimal places. 4 decimal places, so I need to make sure the 5th term is no more than 1 in 10 to the 5th power. Right? Negative 1 to the n over 2n factorial. Okay, so I want 0.0001 accuracy, or 1 in 10,000. Okay, this one starts negative, does it not? Plug in 1. So it goes negative, positive, negative, positive. 2n factorial, 2 factorial, 4 factorial, 6 factorial, 8 factorial. Okay, 2 factorial is 2. 4 factorial is 24. 6 factorial is 720. Okay, you know, some of you actually have a button that does factorial. If you do, great. If not, it's literally 1 times 2 times 3 times 4 times 5 times 6. I'll just show you that. 1 times 2 times 3 times 4 times 5 times 6. 720. Then 8 factorial, I go times 7 times 8. 40,320. Okay, this is not 1 in 10,000, but this is less than 1 in 10,000. So I'm going to add up 3 terms. By adding up these 3 terms, you say, well, you're cheating. You're supposed to add up infinitely many terms. You're only adding up 3. Correct. The error is no more than 0.0001. That's what the alternating series estimation theorem says. Quite powerful, right? So that means you don't have to add up infinitely many terms, which you normally can't do, right? So just do these 3 in your calculator, negative 0.4597, and that's my answer. Show that to you, because otherwise I'm just about done. Negative 0.4597222 so on. Okay, so I know the true answer is somewhere between negative 0.4598 and negative 0.4596. So that's what it says. Okay, and believe it or not, I think I'm done with 11.5, folks. So schedule-wise, we're fine. Let's see, I wasn't supposed to start 11.5 until tomorrow and finish it on Monday, and I'm finished today, Wednesday the 10th. So we're good. So I think I'm a couple days ahead, okay, which means tomorrow I'll probably just give you the quiz and lecture very little on the next section. The next section is a little bit tougher. I'll just give you a heads up on where we're headed. Okay. 11.6 is something called absolute convergence. And then you have something called the ratio test and the root test. Absolute convergence. You should think of absolute convergence as absolute value convergence. Okay. That's what's going on for absolute value convergence, absolute convergence. Okay. So I'll show you where we're headed in the text. Page 737. Absolute convergence, ratio, and root tests. Okay, so definition: the series is absolutely convergent if the series of absolute values is convergent. So don't think of this absolutely in the normal English sense of absolutely, you know, when we say something is true absolutely, okay, you should really think of this as absolute value convergence. Okay, the language that's used is absolutely convergent, okay, but it's more meaningful, I think, if you say absolute value convergent, which means take the absolute value of all the terms, make them all positive. If that new series is convergent, then the original is called absolutely convergent. Okay, so we'll talk about absolute convergence starting tomorrow. Okay, but otherwise I'm done, folks. Schedule-wise, I wasn't supposed to finish 11:05 until Monday, and I'm already done today. Okay, so I'm technically maybe 2 days ahead just on the schedule, but it's nice to do that. I don't think I'm going too far ahead in case I fall behind or get sick or my internet goes down and so on. And we're gonna be okay. So we'll probably end early tomorrow also, and I'll give you the quiz. Quiz tomorrow because Friday's a holiday. Do 11:59 p.m. tomorrow, Thursday, the 11th. Okay, so I'm done, folks. Anybody have any questions? Let me stop the share and check the chat. Otherwise, we're done for the day. Any questions, please? All right, we're done for the day, folks. So have a good day, and we'll see you next time. Okay,
All right, have a good one.
Okay, bye, everyone.